Now student, we are going to discuss question number 10.3, and in this question, this is a question related to fill in the blanks part, and in this question it is given to you number A. Surface tension of liquid generally fill in the blanks with temperature. So let us try to understand. This is the general logic. If we increase temperature, definitely surface tension decreases. Clear? So direct answer we have for this question. Surface tension of liquid generally, I can say, decreases with temperature. Clear? So as the temperature increases, I can say surface tension of liquid decreases. Why? Because as the temperature is increasing, we can see the bonding, or we can say the cohesive force between the molecules is getting weaker and weaker. Clear? That's why we can see here that surface tension is decreasing. Clear to you? Yes. Now if I am talking about part number B, in part number B it is given viscosity of gases increases with temperature. Why? Viscosity of gases increases with temperature, whereas viscosity of liquid decreases with temperature. Why this is happening? Because we know if we are talking about gas molecules, so gas molecules are having random motion, and as we increases temperature, definitely the randomness of gas molecules increases. Clear? So more is the temperature, more is the randomness of a gas molecule we will found, and as well as we can see viscosity increases. Clear? But what in a liquid? As you increase temperature, the bonding between two liquid molecules, it decreases, it getting weaker, and we can see at the time viscosity of liquid decreases. Clear to everyone? Clear? So this is all about part number B. Now if I am talking about part number C, in part number C it is given for solids with elastic modulus of rigidity, shearing force is proportional to shear strain. Clear? Why? Because let's suppose if I am saying to you stress is equal to modulus of rigidity, let's suppose K, modulus of elasticity K times of strain. Clear? So if I am talking about shear stress I can say F shear divided by area. This is equal to, here we will find modulus of rigidity. Clear? Or you can say shear modulus, and I can say multiplied with strain. Clear? So if I am talking about shear, if I am talking about shear force for a solids. Clear? So for a solid, shear force is directly proportional to shear strain. Clear? So here we are getting answer. This is shear strain. But what will happen in liquids? Clear? So actually, definitely, let's suppose if I am talking about these two layers. Clear? And let's suppose here liquid layer is in contact, and let's suppose this is ground. Clear? And let's suppose it is at a certain distance d, and here we are having velocity of a liquid, that is v. Clear? And here we have velocity v equal to 0. Clear? So in fluids actually we define velocity gradient. What we define? Velocity gradient, and we can say this is defined as delta v by delta. We can say this is defined as delta v by delta t. Clear? So now we can say important part we have. How can we define rate, or how can we define shear force related to fluids? So definitely we can say it is defined like this. I am just writing here. It is defined like this. Just a minute. Yes, I can write like this here. F by A, this should be equal to neta delta V by delta T. Clear? So now we can say here this force is defined as rate of shear strain. Clear to everyone? This force is defined as rate of shear strain. So here we are getting our answer. This is the rate of shear strain. Rate of shear strain. Clear to everyone? Yes. Now if I am talking about part number D, so in part number D it is given to you. In part number D it is given, just a minute. Yes. Now if I am talking about part number D, for a fluid in a steady flow, the increase in flow speed at a contraction follows. Now listen carefully. Let's suppose if I am talking about this type of cross section area. Clear? And let's suppose I am saying here, first I am taking this section 1 and 1 dash. Clear? Let's suppose this is 2 and 2 dash. Clear? So definitely we can say here, let's suppose the liquid is flowing from this side and it is going outside from this side. Clear? So definitely we can say if we are talking about steady flow, clear, and we are assuming there is no loss due to this pipe walls, at the time we can say conservation of mass we can follow, clear, and according to conservation of mass we can say A1 V1 this should be equal to A2 V2, or you can say you can apply here equation of continuity, clear. So equation of continuity follows conservation of mass, clear. So definitely we can say in this question we have answer conservation of mass, clear. Now if I am talking about part number E, so definitely this is just a theoretical question we can say. For a model of a plane, let's suppose if we are simulating a model or simulating a model for an aeroplane, okay fine, in a wind tunnel, fine, turbulence occur at a speed, turbulence for a actual plane, so correct answer we have that is greater, clear. So actually let's suppose we have a wind tunnel, and in wind tunnel we are actually simulating same situation as for an aeroplane that we will find at a certain height, clear. So definitely here we can simulate, but here turbulence will occur at a greater speed compared to turbulence that occurred at the actual position. Why this is because here we can say if our model sustain for a greater turbulence, definitely it can sustain for a certain height also, clear. That's why we can say turbulence occur at a greater speed compared to actual situation of a plane, clear. So this is all about this question.